Okay. I'm tired. Conjugate. We should clicker to turn the slides. Do they not have one? Conjugate. Where is the note? This is chalk. Okay. I don't want to see this ever again. Jacobi Gauss-Seidel. Jacobi. 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 Richardson iteration with SPD matrix A. Yeah. How did this happen though? Rho or G? How did this happen? Let's go back to that wretched slides. These disgusting slides. Let me just fucking assume and move forward. I'm not really into this. I want to do conjugate. I want to do conjugate gradient. Conjugate gradient. Conjugate gradient. In the following, A is SPD. Why you always make this assumption, man? I do not like it very much. Formulate solving Ax plus B as the optimization problem. Why, bro? How did you come up with this? And minimize fx. Because A is positive definite, the function f is convex. It is sufficient to look at the gradient. Because A is positive definite, this is always positive. So the gradient of f of x is yeah. Why is this the gradient though? That's my question. B transpose x gradient is equals to B according to them. So A transpose x will be A transpose x, just this, just in chain rule, and then x transpose, so this is also x transpose C gradient is C. Is it the case though? That's what it seems. That's what it seems to me. Okay. So for an SPD matrix, the gradient is Ax minus B, and that's the negative residual. Or if I put this to 0, then Ax equals to B. So whatever is the gradient, whatever gradient is 0, so therefore the minimum of this problem, the minimization, min, minimum. What is the benefit of this point of view? Why I wanted to do this as a minimization problem? Because now we can we can use optimization algorithms. Our first try is applying the method of steepest descent in the direction of the negative gradient. So this is gradient descent. What happens to the residual? At every instance the residual is this. All I'm doing is creating an iterative method here again, like this is an iterative method. I choose alpha k is this, and the step, and xk plus 1 is xk plus alpha k rk. Alpha k the residual, but I mean I'm updating in the direction of the residual. This seems awfully close to the one we just did. Ax equals to b. Ax equals to b via the Richardson method. Richardson boy, right? This seems awfully close to that because we are updating in the direction of the residual. This is the same. This is same as Richardson iteration with damping alpha k. What is the difference between alpha k and the damping parameter? Let me recall. For the Richardson which my optimal damping was 2 divided by 2 minus lambda max of g minus lambda min of g, and both of these numbers are less than 1. Was this correct for Richardson? Yes, this is correct. And because G is just 1 minus A, identity minus A, this becomes 1 minus lambda min of A, 1 minus it becomes lambda max plus lambda min. Is correct. I remember this formula. 2 divided by 2 minus lambda max g minus lambda min g. This is true for all. This is true for all g, right? Find the optimal damping parameter for all g. Yeah. So what is the difference between alpha k and omega? Well, number one, omega is a fixed number, doesn't change in every iteration, where alpha k changed in every iteration. Second, omega depends on the eigenvalue of g, where alpha k just depends on the residual and the matrix vector product A times the residual. First, let us derive this also. Right? What I want to do is I want to get to these. I want to write alpha k in terms of this. So f of xk plus alpha k rk is equals to half xk plus alpha k rk transpose A xk plus alpha k rk minus B transpose xk plus alpha k rk. This is this, right? Alpha k rk, let me verify. Now I want to minimize this with respect to alpha. So I want to find an alpha k such that if I'm given an R update, I mean I'm given a direction R, I want to find alpha which minimizes this. So this should be 0. So how to go about doing that? What can be the intuition for this? Yes. So an alpha, this will be, so for example, let's say, let me bring up a picture, okay? Like this. So as you can see, the blue line is the gradient, right? Let's forget the conjugate, just look at this. So I update in my direction RK, I could have gone all the way anyway. But I wanted to go and look at the minimum. I want to go and settle in the minimum, which means that my gradient of f at this new point is perpendicular to my direction of the update residual equals to 0. I got it. Nice intuition. So RK transpose gradient of f at xk plus alpha k RK will be 0, because the gradient at this new position is orthogonal to the direction in which we came. Because if it were not the case, then I could have moved more into the direction of the gradient and I could have gotten lower somewhere, you know. So this is the case. Yes, now I have understood my everything. Understood the everything there. Right? And what is gradient of f? Well, the gradient of f is just the negative residual. That's how the gradient is defined. Gradient is just negative residual. And negative residual is a x minus b, right? So axk plus alpha k rk minus b times rk transpose equals 0. Right? So rk transpose axk let me just put that in bracket plus a alpha k rk minus b equals 0. Axk minus b or is minus rk, so rk transpose a alpha k rk minus rk equals 0. Yes, I am doing right, everything correct here. I'm not doing anything wrong. I should not doubt myself. Alpha k rk transpose a rk is equals to RK transpose RK. So alpha K is given RK transpose RK divided by RK transpose A RK. I should think loud though, but I want to generalize this though for all directions, not just residual actually. Right? I should generalize this. Let's say I'm at a point xk, I move to a point x prime, which is xk plus alpha k pk, right? A general direction pk. So my thing is that I am moving in this direction pk transpose. It should be perpendicular to my gradient at xk plus alpha k pk, right? This should equal to 0. This will give me the ideal alpha k. But my gradient at f is nothing but the residual or the minus residual, which is a times xk plus alpha k pk minus b, ax minus b equals to 0, pk transpose. Pk transpose gradient of f at this new position, gradient of f at this new position is just ax minus b at that new position. Okay, boy. So let me split pk bracket. I'm not gonna mess with pk. Axk minus bk. So let me write this as a. Let me alpha k. A alpha k pk minus rk equals to 0. A alpha k pk, right? Because axk minus b is again the residual at kth position. So this is how it forms to be the built to be. So my alpha k, my alpha for the next step, pk transpose rk divided by pk transpose a pk. Pk transpose a pk. Is this correct? Let me look at. Yes. Pk transpose r, pk transpose a pk. So given any general direction, now I know the alpha which will minimize xk plus alpha pk, right? Right. Hamiji. So this is the first step. Like first step is to choose pk directly in the direction of the residual. That's it, right? So I'll substitute my pk as rk. And updating directly in the direction of the residual, this reminds me of the Richardson iteration, right? In which every iteration what we do is just update in the direction of the residual, but with the constant omega or with the constant damping parameter. Here we can vary the damping parameter to make it the minimum in the direction of the residual. That's all. Every time we are going to go to the minimum of the residual. Yeah. For the steepest descent, if A is SPD, we obtain this relation. Why, bro? Can you prove it to me? No? Then I don't want to talk to you. Proof is bored. Proof is bored. I am bored. Alright, stop it. You're not funny. You're very funny. Let's look at the proof. For SPD A, show that fuck is this, bro? I know what that is. That is the fixed point, or the minimizer. In K steps, the difference, the error, is this the error? Yeah, that is the error. The error is less than equal to this factor K power in the first iteration. So xk plus 1 as a function of alpha is xk plus alpha rk, where rk is the residual, well, the residual is just b minus a, or ax star, which is b minus ax. That is correct. X star minus xk plus 1 is, subtract x star minus this equals to, I can pull it out, identity minus alpha a times x star minus xk. So the error in the k plus 1th iteration is 1 minus alpha a, error in the kth iteration. And then the error 2 norm, error in the A norm is this. Now because A is SPD, we have orthogonal eigenbasis, therefore EK can be AIZI. अरे क्या है ये बैंचोद? Why do I set alpha prime as that? Why? This I think is motivated from the Jacobi thing, where I write alpha prime as 2 divided by alpha min of A plus alpha max of A. Is that what's happening here? Let's see. I said alpha is that. I get some things which I'm not sure how to understand. What the hell is this? Why? Steepest descent. Steepest descent alpha k and minimizes for minimizer. Steepest descent alpha k that minimizes. Use for minimizer x star. Fx is fx star plus half. if I could do it on the homework, I can do it now. So let me prove this. Let me prove this. Let me prove this. Prove this again. Let me prove this. Proof. I'm very tired. I'm losing my mind right now. Yeah, this video is not for this. I'm gonna age restrict this video because you're watching a person lose his mind. You know, this is what CS major or math major, I guess, does to you. So I am satisfied up till here. I am okay. Can you see this? Like, I'm sure YouTube will be able to see it. Xk plus 1 is xk plus alpha rk, where alpha is just this one. I just see the errors, and this is what I get. Like, the error is x star minus xk plus 1 is equals to identity minus alpha a x star minus xk. So error in the after the kth plus 1 iteration is identity minus alpha a error in the kth iteration, right? Now this is a function of alpha. By choosing alpha such that so error in the k plus 1th iteration as a function of alpha is this bullshit. Okay. I want to write my error ek in terms of the eigen. For example, A is a SPD matrix. So A has eigen, let's say, what's the Z, right? Z is the eigenvectors. So AZ equals to Z lambda. Okay, boy? And Zx is, let's say, okay. Az is Z lambda, and let me, I don't want to, I am not comfortable because I am not understanding this notation very clearly. I am going to develop my own. Zx is, let's say, error at the kth term. Let me not use x as a notation. Z is the eigenvector, and I want to write these coefficients. So he has written these, he has used coefficients as a, right? But that's, so let me use alpha, yes, or small a. Z small a is ek. What does this mean? Let me just convince myself that I am doing something not extremely wrong, which is like my mental state is not. So this times the first one. Yeah, I think this is correct. The first, so I multiply this. It's a linear combination of all of these columns, right? Yeah, it's a linear combination of all of these columns. ZA is EK, that's what I'm writing. And can I write that? Can I write that? Because Z is an ortho, A is SPD, so it's orthogonal eigenbasis. And it's an eigenbasis, that's the key thing. Like, I'm gonna write this here. AZ is Z lambda, Z transpose Z is 1, or identity, I'm sorry. And yeah. So let me write again. E k plus 1 as a function of alpha is identity minus alpha a z times small a. Right? That's my error. That's me defining the error. Small a is just, oh, I want to use some other notation. I can't use alpha. I cannot use. Let me just use k. Okay, I'll remember it. Now I want to look at its norm in the ath square product. which is defined as this as an with the A, and it is just E transpose AE, right? Right. So let me just take a transpose of this. It's small a transpose Z transpose identity minus alpha A transpose times A. Well, A transpose is equals to A. So identity minus alpha A is again a symmetric matrix. So I can skip that. And again, identity minus alpha A Z A. I want to split it up. I want to open this sheet. Now if AZ equals to Z lambda, then Z transpose A transpose is equals to lambda transpose Z transpose, and A transpose is just A. So Z transpose A is lambda transpose Z transpose, but lambda transpose is just lambda. So Z transpose A is just lambda. So yeah, technica, yeah. I want to get to that. I want to do that. I can see it happening though. I want. How do I don't want to open this, man. I'm scared of opening this bullshit. You know what? Let's just do it. Let's do it. Let me just look at this bit. It becomes A times Z minus alpha AZ times A, right? What did I write? AZ is Z lambda, right? Cool. So this becomes Z minus alpha Z lambda with the A, and let's me bring these A's ins, and this is AZ, which again becomes Z lambda, so this becomes lambda square. Is there a lambda square somewhere? Shit. AZ Z lambda, no, with an A multiplied here. So this becomes Z lambda identity minus alpha lambda times A. Is there a 1 minus alpha lambda? There is a 1 minus alpha lambda multiplied with A. Okay, I'm doing it. And I multiply it with, I pre-multiply it with A transpose Z transpose identity minus alpha A. I'm scared. I'm genuinely scared of doing stuff here. I'm scared. And we bring the Z in. A transpose, Z transpose, Z minus alpha, Z lambda, it's not A though, lambda 1 minus alpha lambda A, right? Z lambda, okay, let me leave Z lambda as it is. In fact, let me bring Z transpose in. So this becomes A transpose identity minus alpha lambda identity minus alpha lambda A. Got it. This becomes lambda ai square lambda I times ai square 1 minus alpha lambda alpha I, whatever that means. Oh man, no, alpha is just a constant, right? So alpha lambda I square. Bhai, I am a math god. Summation of I. Yeah, so I got it. This is the error in the as a function of alpha. This is norm of ek plus 1 as a function of alpha. A in the a in a product is sigma lambda j a j 1 minus alpha lambda j square. Yeah. Now what I want to do is set alpha as y. Why? At every time my alpha is different, right? Why? Is this motivated from here? Is this understandable? At every iteration, why do I set my alpha as 1 over y though? Why? Oh, he just set it. If I just set this, I just said it. I just said it. I hope the video is recording. 2 divided by lambda 1 plus lambda n. So this goes on lambda minus lambda n square, and then this is okay. I don't have a problem with that. I don't understand the next steps though. The moment I say I don't have a problem with that, I'm losing my shit, bro. I'm actually gonna unravel here. Steepest descent alpha k. So this is the property. Given that alpha k, if I substitute alpha k, alpha hat, I'm so confused, is going to be lambda 1 minus lambda n over lambda 1 plus lambda n whole square ek a norm square. Like this norm is less than equal to this factor times the previous error norm. Now the next thing that I want to see that I remember, or I want to see that if I could do it before, I could do it again. That is fxk is f of x star plus half x minus x star norm a norm, right? Nice checks. F of x equals to half x transpose ax minus a transpose, no, x transpose b, right? Minus b transpose x. Well, how will I remember this, bitch? How will I remember this? How? This is b transpose x. How will I remember this? Okay. So yeah, what was I doing, man? I want to do it for x star. F of x, the minimum is half x star a x star minus b transpose x star. Let me subtract these two together from Yamina. And what is half x minus x star norm squared is x transpose minus x star transpose a x minus x star, right? Divided by 2. Divido by 2. Belly. Well, x transpose a x, I add let me see homework 4. Let me see the steps. I'm a stupid. X star transpose minus x. Question problem 5. Oh, this shit has been shown for only SPD. Boy, is the assumption that A is SPD? Oh, oh, A is SPD, bro. In that case, let me look at the solution again. X transpose, the error, X star transpose A X star is the same, and then actually B transpose X and X transpose B is the same. I'm such a stupid boy. B transpose X and X transpose B is the same, and in that case, yes, now I make sense. Now everything is okay. Now everything makes sense. Okay boy. Okay boy. What is next? Yes. So if this is same, I don't know what I'm saying at this point. Minimizing fx is minimizing f of x is same as minimizing the a non-error. So this yes, it's always less than e cap. So okay, so error is always, yeah, okay, I understand. It's less than kappa. This all of this just comes from the fact that we substituted alpha k as 2 upon alpha 1 plus alpha n. That's it. That's all. There is no other important thing here. That's just gradient, normal gradient, Richardson method. This is Richardson method because we are updating in the direction of the gradient. Let's look at the यार मेरे दोस्तों ने कुछ मैसेज डाला है कटर्स डिनर बोल के bro is literally eating bread अबे यार पागल आदमी okay so what do all methods we looked at so far have in common? All the methods so far use information about xk minus 1 to get xk. What do you mean all the methods you looked at so far? Bitch, you only looked at one, that gradient is, that was Richardson. All information about earlier iterations is ignored. No, ax equals to b, you did it by 2, you're just solving ax equals to b, you're not going anywhere else. So the iterative methods for solving ax equals to b are Richardson, right, Jacobi, Gauss-Seidel, and now this gradient method, which is the the counterpart of Richardson. So in all of these methods, what we do is we only look at xk plus xk to generate xk plus 1, right? We never look at any other information. Fair enough. What else do you want me to look at, boy? What I want you to look at, boy, is what steps you took. How did you get here, brother? That's what I want to look at. That's what conjugate gradient looks at. So let's see what conjugate gradient looks at. Let me check the temperature. No, let me check the battery in my phone, because now I'm unraveling. I'm going crazy. So what do all iterative methods we looked at so far have in common? All methods so far use information about xk minus 1 to get xk. All information about earlier iterations is ignored. The conjugate gradient method is a variation of steepest descent that has a memory. So steepest descent with a memory. Let P1 to Pk be the directions up to step k, then Cg uses the space for the next iterate. So, what, boy? Given a direction Pk, let's see if I can recall from memory. It's P transpose R divided by P transpose AP, right? That's the alpha that minimizes. So given the direction Pk, what I do is I jump to the minimum directly by using this alpha equals to this. The idea of conjugate gradient is that you choose a Pk, you jump to the minimum by this formula. Alpha is the one I derived. I'm so smart. Then what you do is, because you already know that this is the minimum is in this direction, you'll only look at the direction perpendicular to this or orthogonal to this, the plane orthogonal to this, and minimize in that direction. And now that you have covered this plane, these two vector planes, you look at the orthogonal plane to these combined. So let P1 to Pk be the directions up to step k. Okay. Then Cg uses the space x0 plus span of this to find the next iterate Pk. Oh, so xk. And thus xk is alpha x0 plus some constant, some combinations of this Pk. Okay. So it's like okay. For YouTube, this is something that because given the directions up to step k, we look at the entire thing spanned by that and minimum in that entire span. Then whenever we add the new direction, the minimum in the new column span. So the search direction should be linearly independent, so we don't destroy what we have achieved. We have to do the best we can at each step. So f of xk is the minimum of span of P1 to Pk, f of xk. The step xk can be calculated easily from xk minus 1. So if these steps are linearly independent, and I'm finding the minimum at each k, what this guarantees me is that at n steps, I reach the absolute minimum, because n linearly independent vectors, all of them are linearly independent, and I'm going to check this span of n linearly independent vectors. So that would mean that I'm at the true minimum. Convergence in n step, because at the n step we have x0 plus span P1 to Pn, because P1 to Pn are linearly independent, and thus we minimize f over Rn. Okay, boy. So let us start by writing xk as okay, xk, I write xk as x naught plus some combination of the first k minus 1 directions and then the kth direction, right? Right. So it's x naught plus pk minus 1 y, that's just the components, plus alpha k pk, right? Alpha pk. F of xk is f of xk boils down to this, boils down to choosing this, that pk transpose a times pk minus 1 equals to 0. That means, what that means is that I choose a conjugate, my newest this is the strategy. This is like the strategy that the left hand term depends only on y and not on alpha. It can be minimized on its own accord. This one only depends on alpha. So after I choose pk, I do the minimum in the pk direction. This is something that we've done already. In fact, you can see, right? I mean, it has pk transpose r0 divided by pk transpose a pk, something that looks like pretty similar to that. So the mixed term in the middle depends on alpha and y. Otherwise, we could optimize separately for y and alpha. So how should we choose that we can get rid of this? Let's choose a search direction pk such that pk transpose a and pk minus 1 is 0, which means that pk is a orthogonal to all of the previous columns. So pk belongs to the span of ap1, ap2, apk minus 1 perpendicularly, like orthogonal to these ap1, ap2, ap3, like the span of these. And how can we find that? Thus with pk transpose we get this one. The first minimization is solved for y equals to yk minus 1, computed from the step k minus 1. And the minimization to the second is just this scalar. So we computed this already. Satisfy conditions B and C from above. What were conditions B and C? Conditions B and C is that step xk can be calculated easily from xk minus 1, and we do the best we can at each step. We do the best we can at each steps, and xk plus 1 is calculated easy. Just given pk, if I have pk such that pk is satisfying that property, pk is a orthogonal to all the other previous pk minus 1s, then I can choose alpha such that this, and I'm done. I have xk plus 1. So we said that the search directions have to be orthogonal with respect to a. One can show that one implies that p1 to pk are linearly independent, which satisfies condition a as well. So to find the search direction pk, we want to combine positive aspects of steepest descent and conjugate gradients. In steepest descents, what we do in steepest descent is we just choose our pk to be the residual, right? We just residual, and then we do the alpha computation, which is r transpose r divided by r transpose a r. But here we don't do that because we want our new direction to be a orthogonal to previous ones too. So what we do is we stay close to we stay close to the residual, but we also enforce that pk is a conjugate to previous search directions. How can we do that? First I choose my rk, whatever my residual is. no, residual at k minus 1th step, and then I want to, you know, also subtract some things in this such that it is perpendicular to AP1, AP2, AP3, AP4, etc. What I can do is do Gram-Schmidt orthogonalization. I have to basically orthogonalize my R. So PK is RK minus 1, inner product with PJ in the norm A, because I want it to be in A perpendicular, divided by the norm of PJ times the PJ. Right? All I'm doing is just gonna calculate my RK minus 1 and A orthogonalized I'm applying A Gram-Schmidt to that. A Gram-Schmidt. So orthogonalize in the A space. So let's see what happens. Let's see what's the by choosing this A conjugates, by choosing our PK such that it's A conjugate, it's the A conjugate to this and it's closest to the residual. What happens is, let me see some technical stuff here, right? PK is the span of this with such that PK transpose RK minus 1 is not 0. That is, PK is not orthogonal to RK minus 1. For k equals to 1, set P1 is R0, just the first residual direction, right? The first residual direction. For k greater than 1, X star is A inverse B, which does not belong to the x naught plus span of up to k minus 1. Otherwise, we would have solved that. We would have solved that already, right? B does not belong to ax naught plus span of AP1 up to AP minus 1. So B minus A. So R naught does not belong to the span of AP1, AP2 up to APK minus 1. Right? R naught does not belong in that. And there exists PK perpendicular to the span of this, and which also satisfies that PK transpose R naught is non-zero. That means it has some direction in the R naught. Why it is R naught? Let's see. Set PK such that PK transpose RK minus 1 is PK transpose B into AX, that's the residual, and AX is x naught plus PK minus 1 YK. PK R naught minus PK transpose A PK minus 1. So this is just 0. So PK R minus 1 is PK R naught. That's guaranteed. I see. Therefore alpha K is just PK transpose the R naught. This is the PK transpose RK minus 1. So Okay, I understand the conjugate gradient method. I understand it, but I'm not too confident about it. I'm also very tired. It's 9. Should I just head home? Yeah. Slides. What's important here in these results, which we'll do in the next video, what's important in these results is that to calculate pk, I only need the k minus 1th residual and the k minus 1th direction. Why? Can I formulate some intuition on this? Well, the k minus, what I do is I take the residual at every step. What I'm doing is I take the residual, subtract my new search direction from that residual is subtract all of the previously, take a residual, subtract all of the previous search directions and go in that direction and minimize it. Now look at the new residual. The new residual, my RK will be RK minus 1 minus some vector, right? Wait, my PK, I want to form some intuition on this actually. PK is RK minus 1 minus whatever directions of AP1, AP2, AP3 we have, right? Whatever directions of that we have. My RK is, it will depend on how we minimize it. So let me look at that, okay? Let me just look at this. Apply Gram-Schmidt to RK minus 1 so that we obtain PK, that is A conjugate to all of these. So all of them. So we need some following technical statements. CG technical lemma, okay? RK minus 1 is B minus AXK minus 1. That's just a residual. This implies existence of a PK which is perpendicular to the span of this with PK transpose RK minus 1 non-zero. That means some component, this should not be, it should be A conjugate, right? Never mind. X star is my true answer. It's A inverse B. Basically what I'm saying is my R naught, that means my initial residual, the max residual that I have, does not lie in the span of AP1 to PK minus 1. So there exists a PK which lies conjugate to this such that PK transpose R naught is non-zero. Select PK such that P and XK minus 1. So P transpose R naught, and because my new PK is A conjugate to all of these previous search directions, the thing is at my kth, this is what I'm seeing. At my kth step, this is the whatever residual is left right now. My search direction is such that my residual right now is the same that my residual would have been at the start of the in the start of the process for this particular search direction. So this particular search direction has never been, this particular dimension has never been explored at all. And when it's explored completely and it's removed. It's like we are removing dimensions one by one in this process. So P is in the span of 1 to K, P transpose RK is 0. P transpose RK is 0. Yes, because P is my new, P is the new vector and P transpose RK is 0. Okay. RK is the residual after K steps. XK is argument, Fx is this, gives a residual, call it.